Okay, folks, moving forward, we are talking about calorimetry. Calorimetry. So oh no, I just emptied out. Ugh, hold on. Where did it go? Oh my gosh. Okay, so calorimetry comes from the Latin calor, which means heat, and then metry, which is the measure of. Okay, so calorimetry is the study of measuring heat flow. In order to do this, we use devices called calorimeters. To measure the heat in chemical reactions. When it comes to talking about heat and chemical reactions, the term specific heat capacity comes up pretty often. Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degrees Celsius. Okay, the units for specific heat capacity are joules per gram degrees Celsius. Joule is the unit that we use to describe heat, and then gram is the 1 gram, and then the degree Celsius is the 1 degree Celsius. So literally the units tell the story. So how many joules do I have to put into 1 gram to raise it by 1 degree Celsius? So joules per gram degree Celsius. Another thing that comes up pretty often, referred to in your homework quite often, is the specific heat of water is 4.184 joules per gram degree Celsius. I would star this value. It comes up a lot. You have to use it a lot in your homework, so just be aware the specific heat of water is 4.184 joules per gram degree Celsius. It's a relatively large specific heat. Most things have smaller specific heats than water. Yeah, so if an object takes a long time to heat up, it has a large specific heat. And folks, the concept of specific heat is really important, so I want to kind of illustrate this for you. So let's say, imagine I have a 1 gram sample of iron and a 1 gram sample of water. Okay, iron has a specific heat of 4.5 joules per gram degree Celsius. Meanwhile, water has the specific heat of 4.184 joules per gram degree Celsius. So here's the deal. Let's say I want to raise the temperature of this gram of iron by 1 degree Celsius. How much heat do I have to add to it? Well, I have to add a total of 0.45 joules of heat to raise this 1 gram of iron by 1 degree Celsius. Meanwhile, if I want to raise the temperature of water, of 1 gram of water by 1 degree Celsius, I have to add all of this heat, 4.184 joules of heat into the sample. Do you guys notice the change in size here? Okay, so this is really important. It's important to understand that it takes a relatively small amount of heat energy to change the temperature of iron. Okay, all I need to do is add just a measly little 0.45 joules of heat energy into 1 gram of iron, and all of a sudden its temperature will jump up by 1 degree Celsius. If I had added that same amount of heat energy to 1 gram of water, its temperature would not change by 1 degree Celsius. It would barely budge, okay? Because water requires much more energy to increase its temperature. So that concept is really important. Also, I want you guys to understand that this heat capacity also means how much heat it can carry with it. So if I had a hot piece of iron and I threw it into water, it would, let's say for every gram of iron that got thrown into water, it could transfer 0.45 joules of heat energy for every degree Celsius it contained. Okay, so this is how much heat it can transfer to substances around it per gram. Same thing here. Water can transfer this much heat per gram. Okay, so water it needs this much heat to absorb to change its temperature, but it also can transfer this much heat as well. Okay, so if you have really hot water, it can heat other substances a lot more efficiently than really hot iron. Okay, per gram. Okay, so anyway, that's the concept of specific heat, and we're going to continue to work with that throughout this chapter. So you guys are going to see more and more of that. But that's just the first little dip into the idea. Please note of the units right here. We've got joules per gram degree Celsius. If something is just described in molar heat capacity, then we're talking about the heat required to raise the temperature of 1 mole of a substance. By 1 degree Celsius. So no longer are we talking about 1 gram, we're talking about 1 mole. So its units would be joules per mole degree. Whoop. Degree Celsius. Okay, so that's the only difference between the two. So specific heat capacity is talking about energy required per gram, and then molar heat capacity is energy required per mole. All right, so let's take a look at another example here. So we have 10 grams of substance A. Here is our substance A. Okay, we have 10 grams of it, and then 10 grams of substance B. Okay, and they're both heated to 100 degrees Celsius. So this guy is 100, and this guy is 100. And again, we have the exact same mass of each one, and they are both added to 30 milliliter samples of water at 25 degrees Celsius. Okay, so the same amount of water and the same temperature starting out. So this guy was 25 degrees Celsius. This guy was 25 degrees Celsius. Now, let's take a look at what happens. Again, they both started out at 100. Okay, so 100. Our starting temperature was the same, 25. However, the final water temperature is different. So for substance A, the temperature rose from 25 up to 30 degrees Celsius. And then for substance B, the temperature only rose 27 degrees Celsius, according to our problem. So the question is, which one has the greater heat capacity? So give it a pause. What do you guys think? If I put substance A in here, we saw this temperature change. Substance B entered here, we saw this temperature change. Which one has the greater heat capacity? I hope that you selected substance A. Okay, substance A is going to have the greater heat capacity because it can carry with it more heat energy per gram than substance B, because we saw a greater increase in temperature of the sample A. Okay, so that means that each gram of substance A was able to transmit more heat energy to the water than substance B was. Okay, so that means it had a greater capacity to transfer heat. So now that you guys seen a couple examples of heat capacity, go ahead and pause and try and answer these U-tries. Here's a little chart to reference right here, and then take a look at these questions, take a minute, pause, answer the questions. Okay, for question number 1, you should have said that lead is going to have the greatest increase in temperature. If you guys notice, lead has the smallest specific heat, which means it requires the least amount of heat to enter the substance before we see a change in temperature. So all it takes is a little bit of heat, and then all of a sudden the temperature of lead has already increased its temperature. Meanwhile, water, you have to put a ton of heat into water in order to get its temperature to change. Okay, which answers the question for number 2. Water would have the smallest increase in temperature. All right, next I want to make a metal cooking sheet out of a material that will cool quickly when pulled out of the oven. Which metal listed will be able to cool the quickest? So just like we were talking about heating quickly, things that have small heat capacities also cool quickly. If you think about it, lead only has to lose 0.13 joules per gram in order to drop in temperature by 1 degree Celsius. So not only does it heat quickly, it also cools quickly. So lead will also be able to cool the quickest. Okay, and then the metal that would cool the slowest, let's see, we only have 3 metal options. So the metal that would cool the slowest would be the iron. Okay, because that would have to lose more heat energy per joule in order to drop in temperature. So that is specific heat. If you have more questions, feel free to ask me or Mr. Leiter. Onto calorimeters. Again, this is how a calorimeter, again, is a device used to measure heat changes. In our science classes, we guys hopefully will be able to have time to do this lab. We do a coffee cup calorimeter lab. Coffee cup calorimeters are pretty accurate. They're used to measure, used to measure the heat of solutions. So when there's liquid stuff reacting to each other, we can use a coffee cup calorimeter to measure the change in temperature. So literally it's just two styrofoam cups stacked on top of each other. Okay, so this is like a cross section. So here's your first styrofoam cup and your second styrofoam cup. You just nestle them in each other to make sure that everything is nice and insulated. And then you put your little styrofoam lid on top. These are very high-tech devices, but I promise they work pretty well. Once you've got that, I'm going to move this down a little bit. What you do is put a thermometer through the top, through a little hole. Okay, this thermometer is used to measure the temperature changes. And this is what you do. You put your first solution in there that contains some type of chemical that you want to react. And then you pour in your second solution. Okay, now you've got two solutions mixing together. And when a chemical reaction happens, it's either going to absorb heat or release heat. And that temperature change is going to be measured on your thermometer. Okay, so that's how coffee cup calorimeters work. When it comes to doing the math, with coffee cup calorimetry, it's going to look like this. Q equals MC delta T. I think a lot of you guys have seen this formula before. So again, Q is the heat associated with the reaction measured in joules. The M is the mass of the reactants involved. C is the specific heat of the substances involved. The specific heat units, don't forget, are joules per gram degree Celsius. And then delta T, do you guys remember what the Greek letter delta means? This triangle? It means change in. So delta T means change in temperature. And we nearly always measure this in degrees Celsius. Okay, so let's take a look at a few examples of how Q equals MCAT is used. Okay, so here we go. We've got this coffee cup calorimeter. We are going to pour, I'm going to give you guys a little visual here, 50 milliliters of an acid and 50 milliliters of a base into our solution. Okay, so 50 milliliters of each one. Okay, into the same beaker, and we're going to watch them react. Okay, the solutions themselves started out at 25 degrees Celsius. So this guy and this guy started out at 25 degrees Celsius. However, once they reacted, they rose to 31.9. So 25 degrees Celsius, and then the temperature of these solutions rose to 31.9 once they were mixed together. And then calculate the heat of reaction per mole of HCl released. So I actually don't want to deal with the per mole part. Let's just go ahead and calculate the heat of reaction. I want to leave this nice and simple for the first example. So something you guys are going to want to know for these type of problems is that 1 milliliter of water is 1 gram of solution. Okay, that's actually very technically true. At room temperature, 1 milliliter of water will weigh 1 gram. Okay, so if we're looking at 50 milliliters and 50 milliliters, that's 50 grams plus 50 grams. So the total mass of the solution is going to be 50 plus 50. So 100 grams of solution is what we're looking at. Okay, so let's go ahead and calculate the heat released by this reaction. So we're going to be using Q equals MCAT. So heat, again, is Q. That's what we're calculating. Like I just talked about, the mass is going to be the 50 plus 50 because we're mixing 50 plus 50 milliliters together. So that's 100 grams of solution. Because this is happening in an aquatic environment, okay, both of these are aqueous solutions, we're going to use the specific heat of water as the specific heat for the solution. So 4.184 joules per gram degree Celsius. And that's going to be the case, guys, for all of these problems. Unless they give you a different specific heat to use, you should use the specific heat of water if you're dealing with solutions. Okay. And then finally is the delta T, the change in temperature. So 25 to 31.9 is a change of 6.9 degrees Celsius. Okay, so that means the heat of this reaction is going to be 2,887 joules. And I think we can only have 2 sig figs. Yeah, because, well, yeah, because of 25 degrees Celsius with 1 sig fig. So, or I'm sorry, 2 sig figs. So this is going to be 2,900 joules. Now, here's the deal. This is the important part. Do you guys notice that the temperature of the water rose, which means heat was absorbed by the water, which means the reaction itself released heat. So this is going to be an exothermic reaction. Okay, if this doesn't make a whole lot of sense to you, I want you guys to think about it zoomed in. Okay, here's our water. Here's our first reaction, our reactant. So let's call it A. And our other reactant is the base. So let's make that B. Okay, so we have things dissolved in the water, which are our acid and our base. When our acid and our base meet each other, they reacted. And when they reacted, what did they do? They released heat to their environment, which in this case is the surroundings, the water. Okay, so heat was released by the chemical reaction and the heat was absorbed into the water. And that's the temperature that we noticed. We saw the water temperature rise. So that means our chemical reaction released heat energy. Okay, so there you guys go. That's example number 1. Let's take a look at example number 2. This is another type of calorimetry problem you might see. In this case, we have, let's see, we have an unknown metal. We've got 17.3 grams of a really hot piece of metal. Okay, it's really hot. So here's your hot metal. Okay, and it's going to be heated to 100 degrees Celsius, so really hot piece of metal, and then it's going to be submerged in 46 milliliters of water, so 46 milliliters of water. Okay, so 46 milliliters of water, and that's at 25 degrees Celsius is what it started at, and then the temperature of the water rose to 39. And then we want to know what the specific heat of the metal is. Okay, now here comes some concepts, guys. I want you guys to understand that when this hot metal hits the water, the metal is going to be giving heat to the water. Does that make sense? Right? Because it's hot, it's going in the water is colder, so the water is going to be gaining heat, the metal is going to be losing heat. Okay, what I want you guys to understand is that the heat that was lost by the metal is equal to the heat that was gained by the water. Okay, whatever the metal gave up, the water must have absorbed, because we can't destroy heat energy, right? It has to be transferred. So whatever the heat was lost by the metal is exactly what was gained by the water. Okay, the second thing to understand is that if the temperature of the water rose to 39, that means the temperature of this piece of metal dropped to 39, because they're going to be exchanging heat until there's no more change, like there's no more difference in their heat. So this metal started at 100 and it's going to stop at 39. This water started at 25 and it's going to stop at 39. Okay, because they're going to continue to exchange heat until their temperatures are the same, and then the heat exchange is done. Okay, once you have those two concepts done, let's take a look at how they answer the question. We're looking for the specific heat of the metal. In order to find that answer, we first have to figure out how much heat was gained by the water. So let's go ahead and solve that first. So the heat that was gained by the water is equal to Q equals MCAT. So the mass of the water, 46. The specific heat of water, 4.184. joules per gram degrees. Whoop, Celsius. And then the change in temperature of the water was 25 to 39. So that was a change of 14 degrees. Again, if you're confused, I'm plugging into Q equals MCAT, that formula. Okay. So crunching that out, I get an answer of 2694.496 joules. So this is the heat that was absorbed by the water from the metal. Okay, so that also means that this is the heat that was lost by the metal. So now we can figure out the metal information. So the heat that was lost by the metal is negative 2694.496 joules. Okay. The metal, so we're doing Q equals MCAT. The Q is here. The mass of the piece of metal was 17.3. We are solving for the specific heat, so I'm going to leave C alone because that's what we're solving for. And then the change of temperature of the metal, again, was 100 down to 39. So that's a drop of negative 61 degrees Celsius. Okay, so once we crunch that out, we're going to be able to figure out the specific heat of the metal. So the specific heat, which is the symbol C, of the metal is 2.6 joules per gram degree Celsius. Okay, so again, the whole concept here is that whatever the water gained is exactly what the metal lost. Okay, this is positive because it was gained. This is negative because it was lost. This was a drop in temperature because of 100 down to 39. And there you go. There's your specific heat of the metal. Okay, the last type of question you guys might see when it comes to calorimetry is what happens when you mix different masses of water at different temperatures. How do you figure out what the final temperature is going to be? You can actually solve this in two different ways. You can use Q equals MCAT, but I found a way faster way to answer these kind of problems. And here's how we do it. So let's take a look at this example. So we're mixing 19.9 grams of water at 32 degrees Celsius with 26 grams of water at 59 degrees Celsius into the same container, okay? And we want to know what the final temperature is going to be once they are mixed together, okay? So here's the process. For these kind of problems, the first thing you want to do is add the total mass of water together. Okay, so our total mass is going to be 45.9 grams. The next thing you want to do is figure out what percent of the total each portion is, okay, by mass. So in this case, the first sample, so 19.9 grams divided by 45.9 grams, that was going to be 0.433. Okay, so that means 43.3% of the total is the cold water, and then the hotter water, 26 grams divided by 45.9 grams, 0.566. Okay, so now 56.6% is the hotter water. And the last part you guys have to do is multiply each one by the temperature that they were. So the colder water was 32 degrees Celsius. So that's 13.856 degrees Celsius. And then the hotter water was 59 degrees Celsius. That's 33.42. And then you add the final answer together. So our final temperature, oops, not 45, 47. Our final temperature, once these two solutions are mixed together at different temperatures, is going to be 47 degrees Celsius. Okay, so anyway, that's the last kind of calorimetry problem you will see. If you guys, again, have any questions, feel free to refer to answer keys, ask Mr. Leiter, ask me. And yeah, I hope you guys get it. If you have any questions, again, reach out. Thank you.